Good day to Dr. Harris. So today, me and my group are going to present our group assignment that includes 5 questions, and the assignment will teach us about electronics while also requiring us to tackle several difficult challenges. The other questions cover practical elements such as the association between electrical signal amplitudes and sound volume, the distinction between RMS and peak voltage, and the Bakun Dam's harmful influence on society and the environment. Besides that, question number 4 and question number 5 help us to illustrate the calculation and the result by using the software multism.
So good morning to doctor and my friends. My name is Scott Hao-Yuan and my matrix number is B06221056. And today I'm going to present the question 1, which is when an electrical signal is converted to sound by a speaker, the loudness of the sound depends on the amplitude, and how the volume control potentiometer is used to adjust the loudness of the sound. So there's a diagram that shows that the potentiometer wiring as a volume control. A potentiometer is an extended length of regular wire which a regular battery is linked. In the real design, which is the wire length is divided into multiple segments and arranged alongside each other with plastic metal strips connecting the ends. The current flowing through the wire can be adjusted with a variable resistor with a rheostat. The orientation of the wiper may be changed by moving the potential knob, which adjusts the level of resistance between the wiper and the fixed terminal. The resistor may be manually adjusted to determine the potential difference, and the potential difference between any two places in the circuit represent the amount of effort required to transfer the charge from the first to the second point. When a potential difference exists, current flows through the circuit. When an electrical signal is converted to a sound by a speaker, the loudness of the sound depends on the amplitude of the signal applied to the speaker. The fundamental idea behind the potentiometer is the potential drop across any given segment of the wire will be exactly proportionate to its length as long as the wire has a uniform cross-sectional area and a uniform current flow through it. The accuracy of a potentiometer is the smallest variation in potential difference that it can detect. The potentiometer's sensitivity can be raised by reducing the potential gradient or extending the length of the potentiometer cable. So this is all my presentation. Thank you.
Hi, my name is Ong Ting Sim. So now I'm going to continue the next question, that is explain with a suitable diagram why RMS voltage is not the same as peak voltage. So RMS voltage and peak voltage are two different ways of describing the amplitude of an alternating current, also known as AC. And the term of RMS stands for root mean square. So what does root mean square means? So root mean square voltage is defined as the square root of the mean square of the voltage signal's instantaneous values and is often referred as the quadratic mean. Meanwhile, the peak voltage refers to the maximum instantaneous value of any function measured from the 0 volt level. Usually peak amplitude and peak value are the same if the average value of the function is 0 volts. And if the peak voltage is Vp, the RMS voltage is calculated as Vrms equals to Vp, also known as the peak voltage, divided by square root 2. RMS voltage is always less than peak voltage, and the root mean square averages instantaneous voltages is also smoothing out peaks. So below here shows the difference of the RMS voltage and the peak voltage. The AC waveform oscillates between positive Vp and negative Vp, also known as uh, peak voltage. The horizontal line represents RMS voltage level below wave crest, and the blue dashed line represents peak voltage maximum and minimum waveform values. Meanwhile, the red solid line reference to RMS voltage that is always lower than peak voltage and constant across the waveform. The green curved line shows that the sinusoidal AC waveform oscillating above and below 0 voltage over time. And that's all for my part. Thank you.
I want to share about question 3. With suitable description, explain the controversial issue of vacuum in Sarawak. Okay, the vacuum, a massive hydroelectric dam in Malaysia, has been a subject of controversy due to its environmental impact. The dam construction led to the flooding of nearly 700 square kilometers of virgin rainforest and agricultural area, causing significant deforestation and disturbance of local ecosystem. Critics argue that this destruction of the sustainability concept it was intended to promote. The second one is the society consequences of the dam are also significant. Over 10,000 indigenous people, mainly from the Peanut community, has been displaced, leading to feeling of terror and marginalization. The rate of gene engagement with indigenous groups during the dam design and execution phase has attention. Okay. Number three is the political content surrounding the dam is filled with accusation of corruption and conflict of interest, with former Chief Minister Tadmor Mahmood being accused of personally benefiting from the project through family business interests. This raised concerns about the reason behind the dam development and the transparency of decision-making process. After that, the economic viability of the dam is also questioned. Initially envisioned as a stimulus for industrial expansion in Sarawak, the dam capacity has been lower than planned, raising concerns about the financial feasibility of such massive infrastructure investment. Okay, that's all my point.
Okay, so my part will be question 4. So let's start with the circuit analysis. Let's see this circuit. So this circuit have a source voltage of 120 VRMS. Then this circuit includes resistor R1 470 ohm and R2 1 kilo ohm, as well as two additional components, V3 equal to 30 watt and V4 equal to 65 watt. So this question asks us to find the half cycle average voltage between R1 and R2. So firstly, we will start with the half cycle average values of voltage across R1. KVL in a loop having voltage source and resistor R1 and R4. So V1 RMS plus 65 watt equal to 120 watt. So we can get that V1 RMS is 55 watt. Let's see about the value of peak voltage. So we want to find the value of peak voltage is we using V1 RMS multiple with the square root 2. So the answer will be 77.782 watt. Then the half cycle voltage across resistor R1 is using V1 average formula, which is 2 times V peak over pi. So the answer will be 49.517 watt. Then then we will go to the part of half cycle average value of voltage across R2. KVL in a loop having voltage source and resistor R1, R2, and R3. Then V2 RMS plus 30 is equal to 65 watt. V2 RMS will be 35 watt. The half cycle average voltage across resistor R1 using formula is V2 peak equal to V2 RMS times 2 square root. Then the answer for V2 peak is 49.497 watt. So now we're going to find the half cycle average voltage across resistor R2. So we're using the formula of V2 average equal to 2 times V1 peak over pi. Then the answer will be 31.511 watt. So we can already get the answer, okay, using this multism stimulus. Then we can know the output lah. So additionally, KCL is known as a Kirchhoff current law. It defines the sum of current coming is equal to the current leaving or not.
So for the question number 5, a sine wave with an RMS value of 10.6 volt is riding on a DC level of 24 volt. What are the maximum and minimum values of the resulting waveform? We need to prove it using multism software. So for the gated information, V RMS equal to 10.6 volt. So V equal to square root times V RMS equal to 1.414 times 10.6 volt equal to 14.99 volt. So for the maximum values is equal to 14.99 plus 24 equal to 38.99 volt. So for the minimum values is equal to negative 14.99 plus 24 equal to 9.01 volt. So therefore, the maximum value of the resulting waveform is around 38.99 volt and the minimum values is around 9.01 volt.
So as for the conclusion, the research investigates critical concepts and practical implications in electric and electronic activities, with the goal of improving theoretical comprehension and application. This work aims to connect theoretical foundations to real-world applications by addressing subjects such as potentiometer functionality, voltage measurements, and large-scale energy initiatives. And that's all for our presentation today. Thank you.